Hello everyone, I'm Varsha. Today's topic is on microcontroller. Introduction to register allocation. Register allocation is a fundamental concept in computer architecture and compiler design. It involves efficiently assigning variable to the limited number of processor registers, optimizing program performance and reducing memory access overhead. This process is crucial for generating high performance executable code from the source code. Role of register in computer architecture. Registers play a crucial role in computer architecture, serving as a central nervous system to the power processor's operation. These high-speed storage locations provide processor with immediate access to the data and instruction it needs to execute program efficiently by storing frequently used values. Registers help to minimize time-consuming process of fetching information from main memory, dramatically improving overall performance of computer system. Number and types of registers available in processor architecture directly influence the complexity and capability of computers. General purpose register can store wide range of data while a program counter or managing memory address. Effective management of these registers is a focus of register allocation, a crucial compiler optimization that ensures efficient optimization of these limited resources. Principles of registers allocation. Efficient resource utilization. Primary goal of register allocation is efficiently utilize limited number of physical registers available in computers architecture. This involves carefully managing assignment of variables and temporaries to the registers to minimize the need of for costly memory access. Algorithmic complexity. Register allocation is complex problem that involves finding optimal assignment of variables to registers. This problem is known as n-complete, make it conceptually challenging to solve, especially for large and complex programs. Trade-off and decision. Effective register allocation requires making strategic decisions that balance factors such as performance, size code, compilation time. Compilers must carefully weigh this consideration to generate most of the efficient code possible. Graph coloring approach to register allocation. Building inference graph. The first step to the graph coloring approach is to construct an inference graph. This graph represents the live ranges of variables, their inference indicating which variables cannot be assigned to the same register. Coloring graph. With inference graph in the place, next step is to color the graph using few colors as possible. Each color represents unique register and the goal is to assign variables to the registers while respecting the interference constraints. Handling spills. If number of variables exceeds the available registers, some variables will need to spill the memory. The graph coloring algorithm identifies a spill, indicates candidates and insert the necessary load and store operation to handle the spills. Linear scan register allocation. There are three steps. Liveness analysis. Determine which variable are live at each point in the program. Ordering variables. Sort variables by lifetime of or number of users. Allocating register. Assigning variables to the registers in order spilling with necessary. Linear scan register allocation is simple yet effective approach to assigning program variables to the limited set of physical registers available on the computer. It works by first list analyzing variables, liveness to understand variables to need it to keep it up in registers at each point of the program, then orders of variables based on the lifetime or frequency of users greedily assigns their Available registers spilling variables to the memory when necessary. Spilling and reloading strategies. Register spilling. When number of live variables exceeds the available number of registers, compiler must spill some variables to the memory. This involves selecting um, appropriate variables to spill based factors like frequency of use and lifetime. Reload optimization. Reload spill variables back into register is a crucial step. Compiler employ techniques like coalescing and load hosting to minimize the number of reloads and improve the performance. Stack frame management. Efficient allocation of stack frame is crucial as it affects both spilling and reloading. Compiler must carefully manage stack layout to reduce memory access and optimization register usage. Profile guided optimization. Hence, compiler can leverage the runtime profiles to guide spilling and reloading decision, further improving register allocation by targeting most crucial code paths. Interference graphs and liveness analysis. Interference graphs are the key concept in register allocation, representing conflicts between variables that are needed to stored in registers. These are graphs depicted when variables live range overlap, indicating they cannot be assigned to the same register. Liveness analysis is the process of determining the variable's live range, the period between it defined and when it is last used. This information is crucial for constructing a inference graph and making optimal register assignment. Be careful analyzing the inference relationship of live range of program variables. Register allocation algorithm can minimize spelling and ensure efficient use of available registers. Register allocation algorithm. Linear scan algorithm is simpler and faster alternative to the graph coloring. It makes simple passover code, assigning register to variables based on their live ranges, which represent intervals in which a variable is active. Chaitin-Bagris algorithm is advanced graph coloring approach that incorporates live range splitting and spilling. This recursively select variables to spill and then color to remaining variables, ensuring number of registers that does not exist in available hardware registers.